So, hello everybody. Thank you all very much for being here today. My name is Alyssa Bielatek, as you may already know. And today I'm going to be presenting, once I move the window a little bit, my second year project that I've been slowly working on for the past about year and a half or so. And so let's start with this title slide. On this slide, you can see the question that my second year project seeks to answer, which is, which spectral lines trace what physical processes in the galactic center? So in particular today, I'm going to be talking about the first results that have come out of this project. I won't be directly giving you a definitive answer for the question that I posed, but hopefully we'll get a little bit closer to answering it today. Okay. So as you may have heard, if you have ever studied the interstellar medium or the ISM of a galaxy, astronomers use several molecules as heuristic tracers for different processes related to star formation in the ISM. In fact, there was a paper that got upvoted today on the archive that I saw that was like using some transition of something as a tracer for dense gas. And I was like, cool. This is actively being talked about in the literature. So I've listed some molecules here that are used to trace a couple different like star formation specific processes like outflows, hot cores, etc. And you'll see the molecules that I listed here frequently used to trace each of these processes. But a problem arises when we try to use these like commonly cited tracers to find processes related to star formation in extreme environments like the one in the center of the Milky Way galaxy. In particular, in the central molecular zone, which is about the central 200 parsecs of the Milky Way. As we can see in the circular figure at right, the really extreme densities and like dynamics of what's going on at the center of the Milky Way make the distributions of these molecules pretty complicated, and it brings the molecules that typically trace each of these processes very far away from sites of star formation. So that makes them much less able to be harnessed as tracers for these processes. So that's a bummer. How do we trace these processes like to find star formation in extreme environments if we can't use traditional tracers? The answer is that we need unique alternative tracers that we are able to apply in these environments in particular. So one way we can find these tracers is to target a region of ongoing star formation within an extreme environment and look for molecules that work as tracers there. We might not be able to see those molecules, like say somewhere in the galactic disk where things are a lot less dense, a lot less extreme, I guess. But in high density areas, like in the center of the Milky Way, in the CMZ, we might be able to find useful tracers for each of these processes there. So a great target for a study like this is the brick, which is the molecular cloud that you might have heard me talking about for a hot minute the last couple of years. The brick is a molecular cloud in the central molecular zone, and here is a picture of it. I should know what telescope these two images are from, the green image in background and purple, but I'm not actually sure off the top of my head. This is just to give you an idea of like the shape of the brick. Looks kind of like a bean more than a brick, but that's okay. Overall, the brick actually doesn't show signs of widespread star formation, except for one water maser that's coincident with one continuum point source, which is at the center of this yellow circle here. And that coincidence there of those two features indicates the presence of some kind of prestellar core or star formation activity happening. So in a way, even though the brick is representative of the temperatures and densities in the rest of the CMZ because that's where it's located, it's actually much easier for us to be able to find new tracer molecules there rather than somewhere where there's like a whole lot of star formation going on and it's a really extreme environment. In fact, we have from previous observations of the brick, we know that this particular pointing at this water maser is representative of like, or it has examples at least of the 4 different processes that we're interested in studying. So that these are shown in the panels at the right. We see there's an outflow associated with this core, this maser core, and there's also examples of diffuse as well as shocked gas. So before I got to UF, Adam wrote an ALMA proposal for a wideband 4-to-1 bandwidth, which just means the highest frequency is 4 times the lowest frequency. A wideband spectral line survey for being taken with the Atacama large millimeter / 7mm array. So it needed to be wideband so that we could get as much spectral bandwidth and thus as much discovery space for molecular lines to try to find new molecular tracers for star formation processes. Needed to be as wideband as possible to increase this discovery space. So the goal of the survey explicitly is to build a toolkit of tracers that uniquely identify each of these 4 processes and not the others. And we ideally want to use this toolkit to look for sites of star formation elsewhere in the CMZ in slightly more complicated environments than the brick, and also in intensely star-forming galaxies, the conditions of which are more similar to the conditions in the galactic center than the galactic disk. So we did it. We got the data. This is, of course, James Webb. Whoa, I don't like how that looks. This is, of course, JWST, but you know, I like the GIF, so I put it in here. We got most of the spectra that we asked for from ALMA, but the 2020 happened, and then we didn't get all of it, but we did get a significant amount. So my job has been to go through and analyze, I'm going to make that go away, analyze these data and see what we can glean from them to try to answer our research question of which lines trace which processes. So the first step in finding these new tracer molecules in our spectra is to answer the question, what is the environment like where the molecules are? And this is important because the environmental conditions of a molecule tell us how the molecule is going to emit and absorb light. So its temperature and the density of the material it's embedded in are important quantities to know. And it'll help us interpret the data that we get from ALMA. And by the way, the data that we get from ALMA are they're in a cube form. That's what I'm going to call them. We have a spatial axis, and then a spectral axis that we get for free with radio telescopes. So yeah. One way we can measure temperature and density in our pointing is by taking advantage of the spectra themselves. So in order to interpret the spectra, we need to use them as much as we can. So in particular, we're going to use a molecule whose emission is temperature sensitive in a measurable way. So like a thermometer molecule. One such molecule is called CH3CN, also known as methyl cyanide. And so there are other molecules that are temperature sensitive whose emission you can look at and glean the temperature from, like methanol is another molecule, CH3OH. But we chose to use methyl cyanide because we have 7 methyl cyanide lines in our delivered data. And you'll notice that I've written ladders here and not like lines, because an individual emission line at a given like quantum number is actually split up into several discrete rotational transitions, kind of like fine structure lines, I think that's the right word, or fine splitting, but not quite the same. It's due to different rotational modes of the molecule being excited in different ways. And in that way, they're called ladders because there's like different rungs of the ladder. So what we can do, so this is an example model spectrum of methyl cyanide. What we can do is take these spectra and make what are called rotational diagrams from them to be able to actually extract the physical information we're interested in, the temperature and the density of the region. So some scientists, Goldsmith and Langer in 1999, figured out that if you plot the upper state column density of a given rotational transition in a methyl cyanide ladder against the upper state energy, essentially like the energy that you need to excite that particular component, plotted against the upper state energy for that line within the ladder, and then you fit a straight line to the points that you've made. The slope of the line is related to the temperature of the emitting molecule. It's the negative reciprocal. And the y-intercept of the line, so the column density when the upper state energy is 0, is related to the total column density of the emitting region. So that's a pretty cool and simple way to extract these properties. So if we can repeat this process, make a rotational diagram for every single pixel in our image, because we have a spectrum for every single pixel, we can make maps of temperature and column density. And that's pretty sweet, because then we can interpret the spectra now that we know their temperature and column density. So in the process of going through all of these different steps of doing this, so making the rotational diagrams, actually extracting the data from our raw data cubes from the telescope, both at Adam's suggestion and to help my own sanity stay alive, I chose to do a lot of my data processing in Jupyter notebooks, which if you haven't used them, they're a good way to integrate blocks of code with prose that explains what the code is doing. I guess they're not really as efficient as a pure Python script, but they did allow me to write what are essentially tutorials for each of the data processing steps that I took. And so the tutorials that I wrote are available on GitHub now, and I'm going to go through each of the steps of them, not in gory detail, but just the highlights. And at some point, I hope to publish them on learn.astropy, which is an astropy collaboration creation. But yeah, so I will go through the 3 tutorials that I wrote now, and the tutorials will take the data from straight from the pipeline form, straight from the telescope, to measurements of the physical properties that we got. Okay, so without further ado, here we go. Unfortunately, we don't know before the fact what the velocity structure of the methylcyanide molecule is in any given pixel. And it's actually quite hard to measure that, because the methylcyanide emission line is not a simple Gaussian line that we can then measure the velocity shift of. It's this ladder. And even often the brightest 2 components of the ladder are blended. We'd much rather have just a simple Gaussian line, kind of like this one, although this isn't quite a simple Gaussian, to be able to measure the velocity, so we can easily extract the signal from any given pixel, as long as we know what the velocity is. So to fix this issue, the fact that it's hard to do it with methylcyanide, we chose to extract the methylcyanide signal using a bright molecule that we found to have a similar spatial and velocity structure to methylcyanide. So we examined cutouts of different molecules and what they look like spatially, as well as what their velocity structure looked like. And it turns out that the molecule H2CS, or thioformaldehyde, was a pretty good match. And thioformaldehyde has essentially, it's not a perfect Gaussian, but it has 1 or only 2 components to worry about. So in that way, it was a lot easier for us to take the thioformaldehyde emission, essentially say, where's the molecule in velocity in spatial space, take a mask from that and plop it right onto the methylcyanide cube to extract that signal. However, there's a slight caveat. To do that successfully, we have to recognize that because the thioformaldehyde line and the methylcyanide line are at different frequencies, we can see this is 135.2. The methylcyanide line was at about 147. ALMA behaves differently at those frequencies. The channel width, as well as the spatial resolution of the telescope, is different for the 2 cubes that the lines come from. So we have to regrid the cubes, both spatially and spectrally, onto one another so that we can get them on the same spatial and velocity grid. So that was the topic of my first tutorial, how to do that signal masking process. And so the outcome of that was cubes that had signal from methylcyanide isolated from the noise around it. So essentially something that looks sort of like this. This is actually what the mask looks like. So we derived this mask from thioformaldehyde. And these cubes were created in a reproducible. So every time you make these masks, they'll look the same way. And the format is also user adjustable. So if you want to change the thresholds of what you consider to be noise and what is signal, you can do that in the tutorials. If I had gone through and done signal extraction in something like CASA, I don't know if this would be a great purpose for it, but I remember in undergrad using my little mouse and drawing polygons around where I thought signal was and where, you know, to pick it out. If I did that, my work would be much less reproducible than it is now. And as we'll see later, and as we can maybe glean from what the methylcyanide spectra looked like so far, the spectra are a little bit too complicated with velocity components to be able to do that extraction by eye. So this works. So here's that mask figure again in the lower left, as well as projections of the mask along each of the spatial axes. So the mask is a 3D structure. Here's the mask if you looked at it face on the lower left. If you looked at it from above, I guess, on the upper left, and then looked at it from the right side on the lower right. So the reason that we actually made these projections is to be able to see the 3D velocity structure of the region. And we can see it's actually quite complicated. There's not just a single velocity component. In fact, if you look at any given region of the image, so this little clump is maybe at 10 kilometers per second, this clump is maybe 20, and this clump, a little bit brighter, is maybe also at 20. There's also more structure beyond 30 kilometers per second that we haven't quite gone through the same analysis process for. But remember this kind of complicated structure, it's going to come back to bite us later. So once we have those cubes and those signal masks of like where the signal is, we can make what are called moment zero maps of the emission for any given rotational component in the methylcyanide ladder. So that just essentially integrates, sums up the emission along the line of sight for any pixel. And so the moment maps have units of Kelvin times kilometers per second. So this is a moment zero map, and these are sums of the cube, integrals of the cube along the spatial axes in the same way. So taking projections of the cube in both spatial axes. All right, so now that we know where the emission is and how much emission there is in what place, how do we make those rotational diagrams we were looking at earlier? Because that's what's going to get us the temperatures. So if you recall from earlier, for each of the individual rotational components in the methylcyanide ladder, we need the column density of the material in that component. So what we can do is take our moment maps, if we make a moment map for each component, and convert from integrated intensity to column density, just by this equation from Mangum et al., Mangum and Shirley 2015. That's just a simple equation that gets us from one quantity to the other. And then we have the y-axis of our rotational diagram. And then the upper state energy for each of these transitions is just known from quantum physics, so you can look it up in a catalog. So we can create a rotational diagram for any given spectrum if we have a spectrum. And we have a spectrum for every pixel in our map, ideally. Then we can fit a line, a straight line to the rotational diagrams. And then from the slope of the line, we can get the temperature. Remember, it's the negative reciprocal. And then from the y-intercept, we can extract the total column density for that pixel. And then we have a map. So here's that same rotational diagram at the bottom of that last slide, blown up a little larger. We can see this is a relatively good fit. These translucent lines are sort of like uncertainties on the fit. The temperature that we get from these four components that got fit is 119 Kelvin. And the total log base 10 of the total column density is about 13. So repeat that for every pixel, and this is what you get: a map of the temperature and the column density throughout our pointing. So you may notice don't put too much scientific stock into interpreting these quite yet. We have good measurements for temperature and column density for some pixels, like the one I just showed you. This is a good pixel. But that is not the case for all pixels. And there are also many pixels that do not have temperature measurements at all. So this is caused by a couple of different things that I'm going to talk about right at the very end. But for now, I will continue on. You may be curious about how I can know if a temperature fit is good or not good. So I personally, like maybe I have some idea of like what a reasonable ISM temperature is, maybe 10 Kelvin or 100 Kelvin. But column density values, I do not have a good sense of like what is a reasonable number. But luckily, we can work backwards from our calculations of temperature and column density to produce what the spectrum should look like if the emitting molecule were at that temperature and embedded in material of that column density. And then once we have a synthetic spectrum for those parameters, we can fit the synthetic spectrum against the data spectrum and see how they compare. And so that'll let us check our work essentially. And in addition to being like a little check, we did it right or not, making these synthetic spectra is the first step in creating a full LTE model of this region. So if we include all the molecules that we identify, essentially we get a spectrum that should match our data spectrum closely. And any differences between the data and the model can tell us, if we're missing molecules, if we've included molecules that are actually not there, or if we've gotten the temperature and column density measurements not quite right. So in theory, we could put all these other molecules in, but for now, I'm just going to put methyl cyanide in these synthetic spectra. And I used my second favorite Python package, PySpecit, to make these synthetic spectra. This was another tutorial. The rotational diagrams was the second tutorial, and making these synthetic spectra is the third. So here's an example of a synthetic spectrum, the red line here, overplotted on a data spectrum. This is for the same pixel we were looking at that rotational diagram for earlier. So this is not like a perfect fit. We can see that the model is underestimating the data for these lower rotational index lines, but it's getting kind of close for like the next three, although the noise level is kind of high. This is just one pixel that I picked out yesterday to try to find a good example. And we have more pixels, I guess, to look at. And so this fitting by eye essentially maybe tells us that this combination of temperature and column density aren't exactly right for this pixel, but that's okay. So we've made a rotational diagram and a synthetic spectrum data comparison for each of the pixels that we got temperatures for in our maps. And again, I'm going to talk more about how we can fix the bad fits right at the end of the talk. But for now, I'll move on to something more exciting, which is looking forward in the rest of the project. Now that if we in theory have temperature and column density mapped for our pointing, we can start to really interpret the spectra that we got to say, what molecules are actually present in this region of the brick? How do we interpret all of the spectral data that we got from ALMA? So way back in summer 2020, I actually started this project by doing what I am calling brute force line identification work. So looking at some different spectra that we made from the data and trying to match lines to molecules in a very, not a naive way, but just very let's get all the guesses we can for what this line could be. We used two different types of summary spectra for this. The differences between them are not really important because they're both not physical spectra. They're not associated with a single pixel. One of them is associated with what the maximum pixel is in the cube as you go through in frequency space, and the other is what the mean value of the image is. But we had pretty much the same batch of molecules showing up in the two types of spectra. So what we would do is we'd make these spectra for each of our cubes throughout all the bandwidth that ALMA gave us. And we searched the spectra for detections, which were just regions of the spectrum that were above 5 times the noise level in the spectrum. So Adam actually wrote this code. So then we would use go to a detection, use an online catalog of molecular emission lines called Splatalog to find lines that were near the center frequency of the detection region, given some velocity range of where the rest velocity could be, or rest frequency could be. And then Splatolog gave us an output of, these are the lines that it could be. We checked the list that Splatolog gave us against line lists for a star-forming molecular cloud in the central molecular zone, much more active than the BRIC, called Sagittarius B2. So these two papers had line lists that we checked against. And here is a figure from one of them showing all of their identifications. So this would be essentially the goal to be able to show at the end of our project. And yeah, we also did some by hand, like weeding out of like off the wall detections, stuff that had like never been seen in space before, that we thought was very unlikely to be seen, or molecules that like Adam and I had never ever heard of. I also had another collaborator, Katerina Immer, working on this with me. I don't remember what institution she's at, but in Europe. So that was really fun to be able to collaborate. So doing that process eventually led us to our preliminary list of molecular species that we see in the data. Here is a list of them, separated by how many atoms are in each molecule. I think I got this right. It's sometimes hard to count. An exciting one here is I didn't realize that there were salt lines until I looked at the spreadsheet yesterday. So potentially we might have some table salt, that's sodium chloride, in this region, which is pretty neat. So none of these identifications took into account the temperature and column density maps that we made, because I did this first, essentially. I don't know if it's actually possible for each of these molecules to be excited at the temperatures and column densities that we've measured. So for that reason, this talk is slightly out of order. But this leads me into the future of the project, which is to say, what's next? So the main issue in our data so far is that there are lots of pixels that we can't measure the temperature for, and lots of pixels for which the temperature that we got is not great. Here's an example of one pixel that is not so good on the right-hand side of the screen. The rotational diagram has some potential fits that are consistent with negative temperatures. And the temperature that we did fit is about 450 Kelvin, which seems kind of warm. And the synthetic spectrum for this pixel also doesn't really match the data that well, even though the data spectrum seems to be pretty well behaved, except for these first two components. So one way we can start to get better fits is incorporating the other methylcyanide ladders into our rotational diagrams. That's just adding more points. If you add more points, you get better fits on your lines, and you're more likely to get closer to the real temperature and column density parameters. We could also go through and measure upper limits for non-detected components. So where the signal to noise ratio is too low to extract actual signal, we can still measure like an upper limit for what that signal should be. That will also help us constrain our fits. But there's also some more like systematic issues, one of which is the fact that we have, if you'll remember back to the signal mask that we looked at, there was all those different velocity components at like 10, 20, and higher kilometers per second. I didn't do any modeling of multiple velocity components. All of the fitting that I did was for a single, assuming like a single velocity for the emission. But luckily there are algorithms out there that will account for multiple velocity components, which can screw up our spectra. So Scouse Pi is one of them, written by a frequent collaborator of Adam, Jonathan Henshaw. And at least I hope that's who wrote it. And so I hope to use that in the future to model these multiple components. And also, like I said, once we get temperature and column density maps that work, we can use those to pare down our line list of like which molecules are likely to actually be seen given temperatures and densities that we measure. And so like we can make those synthetic spectra, like I said, including all the molecules in our list, compare it to the data and say, which molecules did we get right, which are wrong. So that will bring us to the final goal of the project. Once we know what molecules are there, and we have images of each of the molecules, we can try to find new tracers for these ISM processes that we're really interested in tracing in the CMZ. So we can start to do this morphologically by looking at like does the shape of the outflow cavity traced by CO or SIO look like the shape of another molecule's emission? Just like going through by eye and comparing that. But we can also use like more rigorous approaches, something like principal component analysis, to let statistics do that association for us. But yeah, so that's all that I have for now. Thank you so much for listening. I really appreciate it. And I'm very happy to take any questions that you have. I guess I'm a little bit over time, but yeah, thank you very much. Should I stop recording or should I record the questions too?
We can record the Q&A session. Okay. Got a few questions. Let's start with Shivani.
Hey, Alyssa, great talk. I have two questions. One of them is, so you said that you go through the process of identifying lines. I'm assuming maybe by sort of detecting Gaussian emission lines. If you find lines that have no identification in the splatter log, do you know what you do next? Like, do you try to identify it through other means? Do you get in touch with other collaborators to figure out what that line could be? Or is that of any interest to you?
That's a really good question. I'm very interested in that. And there are several lines, both for which Splatolog has given us the output unidentified transition, which is like, this is a known transition that we see, but we don't know what molecule it's associated with. And there's also some that we haven't got any hits in Splatolog for. So I have thought about that previously. One thought that I have is that there are some places where there could be like a line that is present due to the presence of some other molecule at a different temperature or column density that like will be excited if you adjust your physical parameters slightly. So maybe something that I would first try there is to adjust, like make sure that we go back to the drawing board on like the temperatures and column density fits. But after that, I would definitely want to talk to other collaborators and see like, maybe starting by looking at other people's papers to see, have they found a line at this frequency? Because as you can see, some of the papers are very rich in lines. But yeah, I would definitely turn to more experts to see like potential identifications. And we've discovered several of those so far. So
that's cool. So these identifications, like for instance, catalog, they're based on laboratory measurements, or
I think so. Okay. Yeah, so there's several CDMS, which I don't know what it stands for. It's like a center in Europe, I think, and then the NASA Jet Propulsion Laboratory have like Splatolog takes into account like multiple catalogs like that. And I think those are laboratory derived values for like the Einstein A value for the transition and like what the excitation temperature is, etc.
Okay, thanks. That helps a lot. Another question, you might have mentioned this, I might have missed it. And out of curiosity, do you have like a signal to noise value for your observations?
Oh, that's a great question.
Yeah, I'm just trying to like, I'm trying to, I don't know, associate it with the observations I work with and trying to figure out what is the signal to noise you work with usually.
So for these, the methylcyanide lines, maybe we can just do a by eye estimate. If I can remember like one of the noise values that I got, maybe the noise is like 0.3 Kelvin. And the signal, say for this thioformaldehyde line is 16. Let's say 18 because it's divisible by 3. 6. This line has a signal noise ratio of 6 if I'm doing math right. So, I didn't find the best, most representative thioformaldehyde line, or for methylcyanide as well. That's even lower signal to noise. Well, this is perfect because it's a synthetic spectrum, but so I don't actually have a great answer for you of like.
No,
overall.
I think that helps. And I think this is very impressive that, you're able to do so much science.
Thank you.
A little.
Shivani.
Great, thanks.
Okay, Desmond.
Yes, great talk, Alyssa. Just one small question, and you'll forgive me if you mentioned this already, but for your rotational diagrams, you have the main fit in sort of like the bold orange, and then there are several fainter orange lines in the background. Could you say a little bit about what, or remind me what those are, and how you go from like, are the fainter fits being incorporated into the main fit, or like how do those relate to each other?
Thank you for that question. That's a great question that I did not really mention at all. So what we did to get an idea of like what the uncertainty on these fits are is I just used curve fit to get like the best fit parameters, and then curve fit outputs the covariance matrix for the fit, since it's a 2-parameter mx, y equals mx plus b slope and y-intercept. So I used I grabbed values from a Gaussian distribution using those best fit parameters, like a 2D Gaussian, the best fit parameters at the center, and then the covariance matrix diagonal values to like be the 1 sigma or 3 sigma spread. I can get you the function that I use for that. But then I grabbed like 10, I think there's 10 slope values and column density, I'm sorry, slope and y-intercept values from that distribution, and just plotted those. But they don't actually, the lighter orange lines don't actually contribute to the fit. They're just derived from the uncertainties on the fit and shown for, showing what are some possible consistent fits to these data. But thank you for your question.
Okay, one last call for questions. All right, so if we don't have any more from the general audience, I'll ask everybody to thank Alyssa once more, and then we can stop recording and kick everybody else out.
Thanks, everybody.